In this lecture, we will be talking about a file system. So the agenda for this lecture, we will start with talking about a structure of a file system. Then we'll talk about how to implement file systems. Later on, we'll talk about how are we going to implement directories. Then if we want to allocate some space for a particular files in the hard disk, what kind of allocation methods we can use, followed by if there are going to be some free space in the hard disk, how do we manage free space? And to end the lecture, we'll talk about efficiency and performance of a file system and what we need to do in the case of a system crash. So we'll talk about some strategies to recover from a system or a disk crash. So let's talk about files and file system in general. So a file is essentially a collection of related information recorded on a secondary storage. So this secondary storage could be a hard drive or it could be a server that you access on a network. However, it's just a collection of some information that is dictated. What the information that goes into a file is dictated by its creator. Now, this particular video that you are watching is also a file that sits on a server and you are accessing that through a network. You might have, well, you definitely have seen a lot of files. For example, a PowerPoint presentation called term_presentation, an executable file, setup.exe, a text file, data.txt. So they come in a wide variety of types and sizes. These can become bigger and grow smaller with time. And as a user, you can create new files, you can append information to a file, you can delete files. So you can do a lot with files. And I believe all of you have done that. Now, that's a file, and we are very familiar with a file because that's sort of the face of how we interact with an operating system. But on the back end, there's a file system which controls how data is stored and retrieved on a hard disk. So a file system essentially organizes the storage in disk drives, and it can be viewed as a layered design. And we'll talk about how the layered structure of a file system works. Several examples over here. For example, Unix file system, UFS, file allocation table, FAT and FAT32, and NTFS, New Technology File System. These are all supported by Windows. And then we have second and third extended file systems that are supported by Linux. And of course, we have the network file system for network storage. So there are 40 names on this list. I'm just showing a few here. The one thing that we need to note at the beginning of this lecture is hard disks are usually accessed in terms of physical blocks, and they are not accessed byte by byte. So block sizes can vary from 512 bytes to as large as 4 kilobyte or even larger. So we are going to be talking about blocks of memory on a hard disk, and you should note that the size of that block can be a variable. So let's talk about the layered file system. And you see a lot of names over here. It's right at the top, you have the application programs, and all the way at the bottom, you have the actual devices. So let's work backwards. We'll start talking about devices and work our way up to the application programs. So at the lowest layer are the physical devices consisting of magnetic media, motor and controls, and the electronics connected to them and also controlling them. Above that, we have the input-output control. I/O control consists of device drivers. These are special software programs that are often written in assembly language, which communicate with the devices by reading and writing special codes directly to and from memory addresses that correspond to the controller card's registers. Each controller card on a system has a different set of addresses or ports that it listens to, and a unique set of command codes and result codes that it understands. Above the I/O control layer, we have the basic file system. This layer works directly with the device drivers in terms of retrieving and storing raw blocks of data without any consideration for what is in each block. Above the basic file system, we have the file organization module, which knows about files and their logical blocks and how they map to physical blocks on the disk. In addition to translating from logical to physical blocks, the file organization module also maintains the list of free blocks and allocates free blocks to the files as needed. Above the file organization module, we have the logical file system. This layer deals with all the metadata associated with a file. So for a file, there is the actual data and there is metadata, which is essentially the information about the file. This information could be user ID, group ID, different modes of operation, date of creation, date of recent modification. Permissions to the file. Do you have read permissions? Do you have write permissions? So all those permissions are part of metadata that falls under this layer. So everything about the file except the data itself. This level manages the directory structure and the mapping of the file names to file control blocks or FCBs. So FCBs are one FCB per file. These contain all of the metadata as well as the block number of information for finding the data on the disk. So essentially it contains pointers to where the data is located on the disk. And above all, we have the application programs. So an application program could be Microsoft Word, it could be any GUI that you use to do something useful on a computer. So let's quickly summarize these topics in this slide. We have at the I/O control layer, we have the device drivers that manage the input-output devices. The basic file system issues generic commands to the device driver. It manages memory buffers and caches, because at the very bottom we have the devices, at the very top we have application programs. So data is going to move to and from the devices to the application program. And the basic file system, which sits right in the middle of those layers, has buffers and caches that do the following: allocation, freeing up space, and replacement. So buffers are going to hold the data in transit, and the caches, they do what they do best: hold frequently used data in order to reduce response times. The file organization module understands files and logical addresses and the physical blocks. It also manages free space and how to do disk allocation. Next, we have the logical file system. This manages the metadata. So it translates file name into a file number, file handle, location by maintaining the file control blocks. The file control blocks are metadata blocks that contain information about the file. For Unix specifically, we called inodes, identification nodes. So this is a data structure that has all the information, the metadata information about a file. Logical file system also does the directory management. How do you organize the directory? Because every directory will have several files and subdirectories. And also, how do you protect files? What kind of read-write permissions are going to be set for each file? The logical file system layer is going to manage all those. So we can say that layering is useful, as you can see. It reduces complexity because like everything which is hierarchical, we are going to make things hierarchical so that each layer is by itself simple, and we can easily track data movement from one layer to the other. And we reduce redundancy. But because we have so many layers with such a overall a lot of functionality overall, we are adding overhead. and this can decrease performance because the more layers you have, the more layers have to be peeled off to go from devices all the way to application or the other way around. The other advantage of a layered approach to file system is that much of the operating system code can be used uniformly for a wide variety of different file systems, and only certain layers need to be file system specific. Now let's talk about partitions and mounting. So if you have formatted hard disk, you definitely have heard these terms, partitioning and mounting. Partitioning, what is that? Well, physical disks are commonly divided into smaller units called partitions. Partitions can either be used as raw devices, which means no structure imposed upon them, or they can be formatted to hold a file system, meaning that it is populated with file control blocks and initial directory structures as appropriate. So whenever you format a disk, then you start seeing this initial directory structure, and it is also populated with FSBs. So partitions can be raw, which means just a sequence of blocks with no file system, or it can be cooked or formatted, which means that there is a file system in place. So it's essentially a part of your hard disk, a smaller unit of a hard disk. A boot block is a very crucial piece of hard disk because it points to the boot volume or boot loader set of blocks. Those set of blocks contain enough code to know how to load the operating system kernel from the file system. So this is essentially the bare bones of the operating system that is loaded up into the memory at boot time. So that is that is saved at the boot block. Or if you have multiple operating systems on a computer, then you will have a boot management program that allows you to choose from which operating system you want to boot your computer. Next, we have the root partition, which contains the operating system. Other partitions can hold other operating systems, other file systems, or maybe they are still raw, so they have not been formatted for a particular file system yet. But the root partition is where your primary operating system lies. At mount time, okay, so what's mount time? Mounting is a process by which the operating system makes files and directories on a storage device, such as hard drive, CD-ROM, a network drive, available to users so that they can access via the computer's file system. So at the mount time, file system, we are going to have to check for its consistency. We are going to try to see if all the metadata is correct. If it is not, then we will have to have some programs that allow us to fix that and then try again. Or if it is correct, then we mount that particular table and allow access to that file system. Now let's talk about virtual file systems. Since we have many file systems that could happen, so you could have a situation where one particular computer which has a particular file system is trying to access a variety of file systems that are maybe local or they may be on a network. So we are going to need an intermediate file system, which we are calling as virtual file systems. So essentially, it's an interface that allows us to talk to a variety of disk drives or network drives, which may have different file systems compared to what we are currently as the primary. So virtual file system, VFS, on Unix provides an object-oriented way of implementing file systems. VFS provide a common interface to multiple different file systems types. In addition, it provides for a unique identifier called vnode for files across the entire space, including across all file systems of different types. So Unix inodes are unique only across a single file system and certainly do not carry across networked file system. So we need another data structure called vnodes that allows us to carry the file metadata information across different different file systems. So VFS allows the same system call interface to be used for different types of the file systems. It separates file system generic operation from the implementation details, and it implements those vnodes which hold inodes or network file details. So data structures that hold metadata. And now we are going to use vnodes so that that sharing can happen across different file systems. Then it dispatches the operation to appropriate file system implementation routines. We'll take a look at what are some example routines in just a bit. So we have over here a diagram which has at the very bottom, it has disk 1, disk 2, and a network connection here. And at the very top, it has the primary file system interface. So if this file system interface wants to interact with this disk or this network, which are having a different file system. So this is remote file system type 1. We have a local file system type 2 for this disk, and there's a different file system type 1 for this disk. So this could be NTFS, this could be UFS, and this could be NFS. So the virtual file system interface is going to allow us to be able to interact with all those devices that are currently using a different set of file systems. So let's take a look at some examples of those routines. The VFS in Linux is based upon 4 key object types. Those object types are inode, file, superblock, and directory entry. So inode is an object that represents an individual file. File is an object that represents an open file. Superblock is an object representing a file system. And reentry is an object that represents a directory entry. So Linux VFS provides a set of common functionalities for each file system using function pointers that are accessed through a table. And we are going to call that table a function table. The same functionality is accessed through the same table position for all file system types, though the actual functions pointed to by the pointers may be file system specific. Some common operations are listed over here. So for example, if I want to open, close, read, write, and memory map a file, I can use those routines, but inside those routines, I would provide the object as the argument. So for example, I could have those 4 objects that go into these arguments for these routines. So if I am interested in opening a file with a specific object inode, then I would take that object and place it in the arguments over here. So some examples of a function table. All right, so in the next lecture, we'll start talking about directories and allocation methods.